Dialogues, your monthly community call to inspire, inform and connect the integrated photonics community. My name is Johan Smeets and I'm your host today. And I'll be taking you through an interactive program that we put together for you that's all about integration. So first, we will start with a speaker from Phix, Photonics Assembly. I will interview Joost van Kerkhof. He's the Chief Operations Officer from Phix Photonics Assembly. And I will ask him about integration, hybrid integration, heterogeneous integration. Why is it important? And where is the future going? After that, we'll have the usual Who is Who, where we have 3 ecosystem partners that are going to present themselves, and we have the 3 different photonics platforms that we're active in with Photon Delta. So we'll start off with our friends from Singapore, AMF. Dr. Patrick, he's going to tell us more about what they do at AMF and how silicon photonics is used in their markets. Then after that, we'll go to Arne Lijnse. He is the CEO of LioniX International. He will introduce us the silicon nitride platform as well as their proprietary triplex platform. And then last of the Who is Who is Smart Photonics, Mr. Alonso. He will tell us about indium phosphide. Now, after that, we'll have a keynote from Ruud Oldenbeuving from Imec, and he will tell us more about how they look at heterogeneous integration, hybrid integration, the various techniques that are used for that, and their take on the future. So, integration is an important topic in integrated photonics, and we'll discuss that later with Joost as well. Just a short update also on what has been going on here in Photon Delta. Behind the scenes, we're very busy putting up the PIC Summit Europe that will take place, its first edition, next week, Monday and Tuesday. So if you haven't signed up, there's a couple last seats available. We almost sold out. And you can do so by going to the website www.picsummiteurope.com. Over 80 different speakers will contribute to the event. We have around 20 exhibitors, very interesting 2 days lined up with you for example, semicon executives, end users, academia, investors, and so on. Really bringing together that community with the relevant stakeholders that are necessary to achieve the ambitions in integrated photonics. So with no further ado, I would like to start with the first part of our program. Okay, Joost van Kerkhof, can you hear me? Can you please unmute yourself and put your video on?
Yeah, I can hear you, Joran.
There you are. Thank you very much, Joost, for calling in today. Joost, maybe first, before we start, could you maybe tell us a little bit more about yourself and what you do at Phix?
Yeah, sure. My name is Joost van Kerkhof. I'm the CEO and co-founder of Phix. I'm into integrated photonics since 2013, where I started at Photonics, that later was acquired by LioniX International. And from LioniX International, I went on to co-founding Phix together with Albert Hasper, who's now the CEO. And since 2018, we are, as Phix, offering manufacturing services for PIC-based products. So we are an independent foundry model. So we don't have our own products, but we manufacture for for customers, basically, that develop products based on PIC technology.
All right. Thank you, Joost, and thanks again for calling in today. I think, Phix is a very promising company, and already you've shown growing fast. I think also you're moving to a new building. Is that correct?
Yeah. We are currently in a multi-tenant building or incubator building, whatever you want to call it. It's a previous clean room of the university that is shared by different companies. But we are growing out of there, and we signed up the lease for a new building, and we'll hope to enter that or to start using that in the second quarter of next year. And there we have our own 600 square meter clean room that we will build. And in total, we have 1,800 square meter building to our use. So that's a very exciting area.
Yeah, wow, great. Congratulations on that, of course. I think also this growth is, because first of all, Phix is doing a great job, but also the integration is a very important, let's say, step in the manufacturing process of PICs, right? And I think the market is there. Maybe you can tell us a bit more about, what is this integration about, and why is it so important for the PIC industry?
Well, as many people know and understand, what makes PICs, one of the things that makes PICs quite different from electronic ICs is that there is not a single platform that can do everything we want with photonics. So you need actually different types of material systems, different types of chips that you need to combine together into one product in order to get the required functionality. So you need different PICs for generating photons, and there are other PICs that are very good in just manipulating the light. And then even other materials are very good at another way of manipulating, if, for instance, high frequency. So typically, products have at least two, or we have seen assemblies up to like 5 or 6 different PICs in one package. And the combination of these chips require combination on both the optical interfaces. So you need to get light from one chip to the other, and that comes with challenges on especially the accuracy of mechanically aligning these chips. But also the electrical context is becoming a more and more topic, because as in electronic chips, the density and the number of electrical contacts is also increasing, especially in applications like quantum or other areas where you have a lot of different signals.
Yeah, exactly. Okay. I think also before we go into the various challenges, let's see, because you mentioned, so by definition, PICs are a combination of different platforms, and then that's, I guess, depending also on the application for which the system is going to be used, and you also probably need the electronics in order to control the PIC itself, right?
Yeah. Well, nowadays in certain applications, people talk about co-packaging of electronics and photonics, especially in the datacom market, so data transceivers, where you ideally want to get as close to your ASIC that controls basically the processing of the data in the electrical domain as close as possible to the PIC. Because even centimeters of signal creates cost energy, especially transferring that at higher speeds. So this co-packaging is definitely a topic that in those applications is spent a lot of time on at the moment, and it comes with additional challenges on basically integrating the state of the art in electronic packaging with the state of the art in photonic packaging, and not necessarily those two are compatible. So there are always challenges to make these processes work together.
Yeah, exactly. Okay, and when we look at the different ways of integrating these platforms, maybe you can tell us a bit more about that.
Yeah, well, in photonics, we typically use, and I'm not aware that there are, let's call it formal definitions, but if we typically distinguish hybrid integration and heterogeneous integration. In hybrid integration, we refer to if you have dies, different chips that preferably are tested functionally before you integrate them, and you basically integrate them on a die-to-die level. So you take one chip of one part, one chip of the other, and you combine them to a certain extent or multiple into one package. That's typically referred to as hybrid integration. That's the advantages are that you can, as I mentioned, you can start with testing the die so that you know that the chance of ending up having a good product is higher. But of course, since it's die to die, it's intensive manufacturing because you have to do all these steps per process. A newer or more recent ways of doing it is heterogeneous integration, where you actually try to do that more on the front end of the process, where you like typical heterogeneous integration, for instance, of indium phosphide on silicon photonics, is where you take almost finished indium phosphide dies and you place them on a pre-processed silicon photonic wafer, so that you have actually the light from the indium phosphide already onto the waveguides of the silicon photonics, but then the accurate patterning of it, so to do the final alignment, you do actually in a post-processing step, so that you can get all the alignment correctly. And that's and the advantage is that is more suited for high volume. The disadvantage is that you cannot pre-test your indium phosphide stuff up front. So you need to make sure that the yield is okay, and it is quite a lot of details need to be right in order to make that into functional devices. So I think for volume, heterogeneous integration is definitely the way to go. But if you want to have flexibility and a high mix of different applications, the hybrid integration will be definitely the first way of, and that's also the part where now products are being made, like tunable lasers is typically all hybrid integration, but they will coexist I think in the coming 10 years or so, definitely next to each other, and maybe in the future we will go more in the direction of heterogeneous integration.
Okay, so right now also at Phix you're focusing a lot on the hybrid integration, and heterogeneous is something you're working towards too, is that correct?
Yeah, well, since the heterogeneous integration requires actually front-end type of equipment, so that's typically done in the foundry where you make the chips, and we at Phix are a back-end foundry. So we have some customers working on that, and there is some interfacing between the front end and the back end. And it's also for us still an area to look into where this interface is exactly going to be between the front end and the back end. So at this moment we need to work with foundries like Imec and others that are working on the heterogeneous integration, and to basically coordinate and discuss where we could pick up basically the processing from their side. But I think the true heterogeneous integration will be a front end, so a chip foundry level of process.
I understand. Okay, and so when we're talking about the back-end integration that you do at Phix, what you already mentioned a couple of challenges before. Maybe something about the processes, the equipment, the alignment. Can you maybe expand a little bit on that?
Yeah, well, the main challenges are, the general challenges are, of course, try to place or connect chips together in a way that you have a very accurate and repeatable process to do so, because the dimensions of the signal, so the mode field diameters are very small, sometimes just a few micron. So you need to have a sub-micron capable process. And then the second step is to keep it there also after thermal cycling or thermal shocks even. So that's also a design effort that we need together to do with our customers. And then the next challenge in that is to try to use as much as synergy from other processes and design. So it's actually getting into standardization. And I think the first what we are doing now mostly is that we try to at least standardize on processes, so that we use what is a known good quality of a process, and that already helps a lot. But then, we have a lot of different requests from customers on configuration of a design, and it's not always straightforward to apply these processes to all these different configurations. So we are typically in a phase where we see a lot of traction from different directions, and we try to keep it the number of configurations limited on the part that we control, and that are the interface processes.
Yeah. All right. Thank you very much, Joost. I think we are going to move on to the next part of today's session. I would like to thank you for your time. If there are any questions, I will put forward them to you later. Next speaker is Arne Lijnse. He is the CEO of LioniX International. And Arne has been CEO since 2020, and he has around 20 years of experience within the PIC industry, and has been involved deeply with the invention and the development of the proprietary triplex platform. Yes, Arne, can you hear me?
Yeah, I can hear you. Can you also hear me?
Yes, we can hear you too.
Perfect.
If you can share your screen.
I'll start my presentation and share my screen.
Yes.
If I'm correct, you see my screen?
Yes, we see it. The floor is
so
yours.
I got a few slides just to introduce LioniX, who we are and what we do. I'll try to keep it within 5 minutes. As said, my name is Arne Lijnse, CEO of LioniX International. Been with the company since 2005. I was already nicely introduced by the chairman, so no further additions there. So LioniX International is a vertically integrated company, a foundry that makes us a bit different than the pure play foundries. So we specialize in integrated photonics, but we do not only deliver chips, we deliver modules in scalable production volumes. So in photonics, we have a lot of customers who ideally want one or a few devices for testing or for space applications. Of course, the holy grail always is automotive, consumer applications, telecom, where you need millions. In order to facilitate that and provide customers there, you need to be able to use the right technology from the beginning. So therefore, make the modules that you make scalable. We're not a standard foundry that builds its own products. So I always compare it with Lego. We have building blocks with which we make a solution for our OEM customers. The customized solution we do there, as discussed earlier, in scalable production volumes. So we take into account what the volume of the final customer is, and always at the forefront of technology development. And I'll introduce also our waveguide platform. But first, where are we? How big are we? We're in the Netherlands, eastern part of the country. From a global perspective, of course, the Netherlands is just one big city, but there's more than Amsterdam. I'm just saying we're at the other side of the country. Growing, and we've been established since 2001, and we do all our fabrication and production here in the NanoLab Mesa Plus cleanroom. The platform which we talk about today is the triplex silicon nitride based platform. As you see in the nice picture at the bottom, also transparent invisible light, and that also makes it nicely complementary from different waveguide cross sections, and you see different flavors in these pictures. But the nice thing is that they're all made with the same fabrication process. They're all made with the same materials, same fabrication steps, just different geometries. And the triplex technology is very nicely complementary, and Joost already very nicely introduced it from Phix. There is not one platform that can do it all. We need other platforms. And therefore, in my view, always, photonic integrated circuits is not about chips. It's not about which platform is the greatest and what we do there. It's how you build a module. And then a nice example, for instance, are these two modules. These are made for microwave photonics applications for beamformers in satellite networks. And you see that these are renders, but of course, we also made them. And what you see in these pictures, in the central, you see a large silicon nitride triplex-based chip as acting as a true time delay for optical beamforming networks. And on the top left, just go to the screen, this one and this one, those are, and in the other one, you see two here, one is there and the other one is there, are indium phosphide chips. In this case, to generate light, to do high frequency modulation, high frequency detection, all things that silicon nitride cannot do. So what we are very good in is low propagation loss, matching mode profiles, building complex structures where you need large path length or where you need the low propagation loss. But generating a photon in silicon nitride is very difficult, but other platforms like indium phosphide can. So there's a very nice marriage. And the promising part and the uniqueness of silicon nitride is also acknowledged in the rest of the world. And there's a nice research or nice overview paper of actually UCSB, the people behind University of California, Santa Barbara, John Bowers, who is one of the initiators of a lot of silicon nitride research in the US. And actually the low propagation loss measurement of 0.1 dB per meter, which we did in the past, was in collaboration with UCSB. And as you see in the overview, actually, I'm very proud of that 4 of the applications and the modules in there are LioniX inside LioniX technologies. So it's silicon nitride as a complementary technology and as a backbone of photonic modules is becoming more and more important. So if you have any questions, I'll be here. I'll be waiting in the rest of the meeting also. So if there any questions pop up later, feel free to ask.
Thank you very much, Arne. Indeed, if you have any questions, drop them in the chat, and we can get back to them later. Or Arne can also reply in the chat. He has access to that too. So thanks for giving us an insight into LioniX and what you do, and how the silicon nitride platform is being used also in combination with other platforms. I think it's the way it will go forward, being integrated in various combinations that depend on what functionalities are needed in the application. So thanks for your time. We will go back to Patrick. So our next speaker of today is from AMF Singapore. His name is Dr. Patrick Loguotiang. He is the CTO and also co-founder of AMF. AMF stands for Advanced Micro Foundry. He was one of the co-founders in 2017, has over 30 years of experience in the semicon and optoelectronics sector. And he will tell us a little bit more about what they're doing at AMF Singapore and how they use the silicon photonics platform. Mr. Patrick, are you still there? We managed to pull up your presentation, so we can go to you now.
Yes, I'm here, yes.
All right. So if all is good, you can see my screen and 1 second.
Okay, thank you very much for inviting us to participate in this very interesting event. So I will discuss very briefly what AMF as a pure play silicon photonics foundries. Primarily, we have started with the SOI based as the platform, taking on the heterogeneous integration, or say hybrid. I think these two definitions sometimes people use differently. So heterogeneous a lot of times referring like opposite to people like say monolithic. So such as the electronics and the photonics co-integrated is called monolithic. The heterogeneous means you need to integrate a different type of materials, which is not typical a CMOS line material that you see. So like for instance, the previous speaker just mentioned about the indium phosphide 3,5 bonded on the silicon materials. This is one type of a definition. Yeah, and the other one
Patrick, excuse me for the interruption. Can you maybe put on your camera?
Oh, okay. Okay, then the other one is called a hybrid. A hybrid typically means there's the two systems, like the electronics, the chips, and also the optics chips. You put them together. But sometimes the definition gets a little bit smeared because for ready-made laser chips with the silicon photonics wafers also. So, but for now, we are as a pure silicon photonics, the preparation to extend the versatility of the platforms onto both. It's a very similar idea as people in the CMOS world. The investing is keep on like lithography tools. But photonics, we have to think of some way to keep on putting a different type of materials, either through the heterogeneous way or the hybrid type of way. So we're trying my best to touching on both points. Okay, so this is very brief overviews for AMF. So we are the pioneer of silicon photonics development for more than 15 years. Actually, it's a little over 15 years. For AMF as a company, it's over 5 years now. So we have a complete 8-inch lines, manufacturing lines in Singapore. So that line is optimized for the silicon photonics, the front-end chips, as well as we have some MEMS capability here. So that taking care of the optics IOs. So we have 4 material platforms right now we are offering is the SOIs, nitri SOIs, nitri silicons, and also nitri glass. So we have a PDK for all those platforms and custom design support available across all those platforms. We have been doing volume productions for people putting the photonics chip into their modules as a product into the field used for last 5 years already. So we're covering various market verticals for telecoms, LiDAR, data center, and computing. So, right. We have serving the photonics supply chains in quite broad range, like for pre-developed IPs and also those platforms. So we do wafer fabrications that includes the MEMS capabilities for the and also we do testings for both hours for pre-wafer shipment. There's a quality assurance test as well. So all those preparation allow us to start towards the co-packaging platforms, which is very hard nowadays. And we provide various in-house fab support. So this is the platform we can very briefly describe what it means. So standalones, so SOI, nitri, and glass, then combined with the optical IOs for people putting the various type of active source, so on and so forth, then become optical engines. And also we are in the middle of preparations to combining for different materials onto the existing platforms. Then offering we call as hybrid or heterogeneous in a way. So the other definition people give it as an X-on insulator. So this is a very interesting way of looking at it, how the photonics will move. So foundry is one of the difficulty for foundries because we have to dealing with various type of applications. So we have to think very aggressively and also smart how to pick up the material, how to screen the material, then allow us to move towards a different type of platforms to make it more versatile for different type of application. So for the far backend capabilities, what we have for the wafer level, for instance, for the optical I/O preparations, we have V-groove, deep trench, UBM solders, and the laser diode attachment skins. This all comes with all the device designs optimized on the wafer level that in order to work with the fiber and also the lasers. So it's custom. So it can be, we have a standardized cell library offerings and as well as provides customizations for those interface because the fiber and people typically for a laser, they come in with the different forms. So this is the summary of the so-called wafer level toolboxes that taking care of the packaging assembly parts. So the next one is the detailed example how we do the fiber alignments, which is the integrated V-groove, and also with the suspended spot converters, the edge couplings. Next slide. So speaking on the heterogeneous integration, I think the previous speaker just mentioned about the work through the oxide bondings. We have done a similar type of work before, but this is based on the multi-chip pick and place, the multi-chip wafer bondings, again bondings on the whole 8-inch wafers. So what it shows is the picture after the bondings, what the acoustic scan picture that shows, and also the laser performing behaviors. So this one, we think it's become the technique bonding itself become more and more important, because the materials you hear these days, like lithium niobate materials, BTOs, and also some of the other materials in play in addition to the traditional indium phosphide bondings. So the technique itself become a very important tools for us to tagging on the heterogeneous integration now. Next slide just indicates all I described above that allow us to move towards the co-packaging capabilities. The co-packaging capability typically people referring as the electronics optical packaging, but the photonics chip itself needs other level of the material incorporation. This is what the heterogeneous integration come into play and play a very important roles. So both the hybrid and also the heterogeneous platforms, the tool type of tools, type of devices that allow us to make into a whole system become very important to allow us to move to the few generations ahead. Yeah, thank you very much.
All right, thank you very much, Patrick. Very clear presentation. I'm happy we were still able to do it. Then we are moving to our next speaker. And our next speaker is from Smart Photonics. He is an indium phosphide pure play foundry based here in Eindhoven. And Alonso Jesus Milan Mejia, if I pronounce your name correctly. You are the senior scientist and process architect at Smart Photonics, and you've been with them for over 5 years. And Alonso also holds a PhD from the Eindhoven University of Technology. Alonso, can you hear me? And
yes, I can hear you. Let me start sharing my presentation. Yes, well, thank you very much for the invitation. I'm glad to share what Smart Photonics does. So, well, as you have mentioned, I did my PhD at UE. I work on the indium phosphide membrane on silicon, working towards a high-speed modulator with electro-optical polymer. So I think it's heterogeneous at best, or hybrid at best. After that, I started working in the R&D department of Smart Photonics, mostly in new integration schemes. So customers come and they have their own ideas and they want to put it on our line. So I help them to translate that, and also some introduction of new technologies. Those are my main roles here. So Smart Photonics is an independent foundry, and if we see that we try to compare with the semiconductor chain, I think we see that we are quite similar in the role as a TSMC. So we do the fabrication, and our partners do the different part of the design and packaging, as Phix has mentioned. We use the same equipment and the semiconductors. This business model is the same, so it has been validated, and we think that it's a similar economics and of scale and the cost down. So that we see quite a clear growing. Smart Photonics is specialized in indium phosphide photonics integration circuits, and we do it by using a mature PDK. We think indium phosphide is a really nice material because it allows you to have light sources and amplifiers together with the passive and high-speed modulators and other nice photodetectors, so all in the same platform. We support our customers by moving them from prototyping to volume using our production line and a validate PDK. Also, we have a MPW service that allows the people to get quick introduction to our technology after go to production in a really fast speed. We do the monolithically integrated indium phosphide by our PDK. So we have more than 50 proprietary building blocks, and we have worked more than 10 years in refining this PDK. So it's a mature PDK, and we protect it. So we have quite some protection, and we have like amplifiers, lasers, waveguides, passives. So the nice thing is like the customers can start putting this one as building blocks, like Lego, one after the other, and then can create some chips for different applications, like datacom chips, or there are some sensing applications. And by the use of the PDK, I think the designs can be customized really easy. You can reduce the time for market, the leverage or experience, and also the leverage or infrastructure. So they don't have to build up their own fabs. They just use our fabs and processes for that. I think for a hybrid, I think we see two main directions for hybrid. So one is we are getting our chips are more complex, more high density. So the combination with electronics is important also for high speed applications. So that's from electronics and photonics integration, but also from photonics to photonics, we see that there are some, I mean, indium phosphide is a really nice platform, but the other platforms has also really nice properties that it can be benefit for some applications. And in this case, we observe that transfer printing is a nice technology that we consider that it can benefit from the different technologies and allows to add the light sources and amplifiers from the indium phosphide to the other platforms, but also it can be benefit by the low loss passives of the nitrides, of the high density of the silicon photonics. And we consider that this technology has an advantage that can go to production really quick and it can scale really nicely. So as this figure shows that you can really go from wafer to wafer transfer printing or photonic chips into the other platforms. So brief summary is like, well, Smart Photonics is we do Phix on indium phosphide. We do the prototyping and volume production for our customers. There's a large number of applications that use the same technology, but we also see that there are other applications that can be triggered by using the hybrid integration to profit for the performance of the different platforms. And we see that transfer printing is a nice, interesting technology that can really enable a scalable hybrid integration. And I think that's my slides.
So yeah, then I would like to move, if there's any questions later in the chat, we can look at them later, but then I would like to move on to our next speaker. So basically what we did is we looked at the different platforms within the ecosystem. We had a look at the silicon nitride, the silicon photonics, the indium phosphide platforms. We learned from the speakers on what is it that makes these platforms unique and what are the benefits of using them. So what we will do now is we will listen to Ruud Oldenbeuving. Ruud is the principal scientist and R&D manager for photonic systems at Imec, the Netherlands. In his current role, he's responsible for building a new photonics group for Imec in the Netherlands. Ruud, can you hear me?
Yes.
Yes, okay. If you could please share your screen and enlighten us with your presentation.
So, in this keynote, I will discuss hybrid integration with you, and basically, I will cover 3 topics. Why hybrid integration? Of course, we've seen it already, but just a short recap. Then I will briefly touch upon the most commonly used methods of hybrid integration, and I will end with an outlook on where I think that the industry is heading towards. But first, a short personal introduction. My name is Ruud Oldenbeuving. As mentioned, I'm a principal scientist and R&D manager for photonic systems here at Imec Netherlands. I have a extensive background in laser physics and integrated photonics. Started with pretty much the biggest laser in the Netherlands that consists of 2 big rooms connected to each other, just one laser. And as my expertise grew, the size of the laser shrank. So towards later times, I was more focused onto indium phosphide gain materials and lasers. During my PhD, I worked together with LioniX, and I was one of the first, if not the first in the world, to combine indium phosphide and silicon nitride to make a very narrowband hybridly tunable laser. And I've worked after my PhD at LioniX and the different startups from LioniX, and since 2021, I am working for Imec to start a new photonics team. So as mentioned, why hybrid integration? It's pretty much the same picture as the previous speakers show. If you want to do many things at the same time, there's not one platform that can do it all. So by combining the strength of the different platforms, you get the best of all worlds. And it can be, for example, silicon is not very good at propagation loss, indium phosphide is not very good at it. But if you combine it with silicon nitride, you can get multiple routes towards a very good solution. And as an example for that, I want to show some work from my PhD a long time ago. We started off with an indium phosphide chip and a silicon nitride chip fabricated by LioniX. And we were able to achieve a quite good line width of 25 kilohertz, but that was just by aligning. So it could be that you named this hybrid integration. Basically, it was just two separate chips. And later on, by packaging those two same chips, we had 100 times improvement. And we went down to even 200 hertz, or by tweaking the design a bit, we were able to go even down to 20 hertz. Then the different types of hybrid integration. I think the most commonly used still is hybrid integration via lens coupling. So you have single devices and you put a lens in between. It works quite efficiently, but you can only do a few devices per day in production, and the losses are okay. It's not great. So a typical picture that you would look at is shown over here. You have a laser, you have a lens, and then you have some chip underneath. A more efficient way is hybrid integration via edge coupling. Basically, you just cut away the lens and you glue your laser directly to the rest of your photonic chip. This way, you can speed up the process a little, but you're still aligning single chips to each other, and then the losses are, I would say, similar to when you use the lens. And this is an example of such a device fabricated by LioniX, where you have a nice indium phosphide chip and a silicon nitride chip combined to make a very stable and good laser. The next thing, which was mentioned already, is flip chipping. Basically, what you can do is you process a small hole into your photonic chip, and there you flip your laser into that hole. This way, you can do the assembly within less than a minute per device. You can do it on a wafer because you don't need to dice out the chips first. Losses are medium, not as good as when you actively align it with the previous method. And as an example over here, we've shown that this can be done on a wafer. We've etched all these gray elements over here. Those are holes etched in a silicon wafer. And we were able to flip indium phosphide tiles onto some pillars, and we've done this quite efficiently. The next thing which is in line is hybrid integration via microtransfer printing. It's pretty much the same process, except that you don't have to etch in your waveguide chip anymore, and you can do many of these devices at the same time. The losses are very, very, very low. So this has very high advantages over most of the other applications, I would say. And as an example here, you see a SOA, that's a semiconductor optical amplifier, which is micro transfer printed onto a silicon waveguide, which is the gray line underneath. Afterwards, the metallic lines were deposited to make an actual device out of it. So what does the future hold? In my opinion, the future holds the next step. That means electronic integration and photonic integration on the same chip. Most likely, it will not be a full integration of photonics and electronics on the same wafer. And the reason for that is electronics is just incredibly expensive in terms of footprint. And photonics is quite large, which means that you have to either throw away a lot of your electronic chip footprint, which is very expensive, and you have to add multiple layers of maybe not very compatible devices together. So I think that the future is co-packaging of photonic and electronic chips. And as an example, this is work done by University of Ghent. And you have a silicon photonic chip where the bond pads are already on the chip, and you just flip a driver for the photonic chip in electronics. You flip it onto the device. And with that, I would like to thank you for your attention.
So thank you for your presentation, Ruud. It was interesting to see the various methods that you described. If we understood correctly, the transfer printing is, let's say, the most promising way to go forward to integrate these various platforms.
It would seem that way, yes.
Yeah, yes, exactly. And do you know, like, is this already something that's being applied on a commercial level?
As far as I know, it's not quite there yet. It's very much in the research development phase, but it seems to be very promising and could become available rather soon, because the machines are there, but the recipes are not tweaked to perfection yet. Okay. But that's as far as my understanding of it goes.
Yes, exactly. And so you're saying when you do this transfer printing, you can do that on wafer level, is that correct? Yeah.
Yes, that's correct.
So that's interesting also when you talk about volumes and
yes,
integrating these.
So you can do it on 300 millimeter wafers. So you can basically, it's a post-processing step. You take a 300 millimeter wafer, fully processed in a CMOS fab, and then you can take known good dyes from indium phosphide chip, for example, for indium phosphide wafer, and you print them all on your wafer.
Okay. Thank you, Ruud. I don't see any questions in the chat yet, so I'd like to conclude your presentation. And if there's any questions in the future, we will forward them to you. So then we are going to conclude the session. The next Delta Dialogues episode is scheduled for the 7th of December. Remember, it's every first Wednesday of the month. So the next one is on the 7th of December, and there we are going to look back at the PIC Summit Europe, which is going to take place next week. We will have in the episode our CEO Evert Roos, but also Ivan Nikitsky from Epic, and we'll have some of the chairs of the panel discussions taking place next Monday that are going to give their insights of their discussion they were leading. So there we'll have Sylvester Latowski from the PITC. He's going to speak about the standardization requirements for high volume production. We are going to listen to Michael Lebby from Lightwave Logic. He is going to lead the discussion about heterogeneous integration. And then we are also going to have John Bell in the broadcast, and John Bell from High-Tech. He is leading the investment and tech transfer session. And so we're very looking forward to look back at hopefully a very successful Phix Summit next week. If you haven't signed up yet for Phix Summit, please do so on the website www.phixsummiteurope.com. And if you want to contribute to the next episode of Delta Dialogues, not the one of 7 December, but the one after that, you can do so by scanning this QR code and filling out the form that's behind it. We accept all ideas and suggestions. If you have an idea you want to pitch, if you have your company you want to introduce, or a certain topic you want us to inform about. So please feel free to do so. You can also find this form on our website. If you go to photondelta.com in the events section, you will see the Delta Dialogues almost everywhere. Click on one of those and you can get access to the form. If you have any feedback on how we can make this more valuable to you, the community of integrated photonics, also feel free to let us know. You would help us a lot. You can scan this QR code, or as similar as with the suggestions for content, fill out the form that's on the website. Then with no further ado, I would like to conclude this session. Thank you very much for watching, and thank you all for the speakers for calling in, and see you next time. Thank you.